A good day to all. Welcome to Power Electronics, and we are dealing with module 5 of electric drives, and this is the second video on this particular module. And we had mentioned before, in this particular video series we are going to deal with CO4. That is, at the end of the video series you will be able to select converters and control schemes for AC and DC drive applications. We had dealt in the previous video with introduction to electric drives, block diagram and advantages of electric drives, and in this particular video we are going to deal with the types of load and the classifications of the load torque. And here you can see the nature and classification of load torque. So this is our first topic, the nature and classification of load torque, and you can see over here the four types of classification of the load torque. You have the constant load torque proportional to square of speed, load torque proportional to speed, and the load torque inversely proportional to speed. As the name suggests, from the name itself, the type of load torque is understood. So constant load torque means you can see over here, even if the speed is varying, the speed is on the y-axis and you have the load torque on the x-axis, even if the speed is varying, the load torque is constant throughout. So you can see over here, the load torque is constant throughout. One of the main examples for such load torque is a crane which is hoisting a particular load. So you have a particular load over here and a crane is hoisting it in the upward direction. So you can see that even if the speed is varying, the load torque present is the same throughout. The load torque present over here, you can see it is the same throughout the particular operation. The second type of load torque is the load torque proportional to square of speed, and you can see over here it is having a parabolic type of shape, and the main example that you can say is a fan. So the load torque is proportional to the square of speed. You can see that in a fan, as the speed of the fan is increasing, the load torque is increasing according to the square of the speed. So this is one of the example. The fan is one of the main example of the load torque proportional to square of speed. The next one is it's not very common. You have the load torque proportional to speed. It's not very common. Now in this particular load torque, you can see the load torque is proportional to the speed. One of the example is a separately excited generator, which is a DC generator, which is connected to a constant load resistance. It's not very common. And the last type of load torque is the load torque inversely proportional to speed. You can see it is having a hyperbolic type of shape. So here our load torque is inversely proportional to speed. One of the main example is paper mills. Okay, so in a paper mill you usually have constant power applications. So power in terms of torque, what is the equation? P is equal to T into omega M. So in this particular application, you need to get constant power. So you can see that if the speed is increasing and you need to maintain the constant power, you need to maintain power as a constant. So if omega M is increasing, then the torque should reduce. Only then you will be getting a constant power application. So from this particular relationship, you can see that as the speed is increasing, the torque is reducing. If the speed is reducing, your torque should increase. And that is why you can say that the load torque is inversely proportional to speed. And we have seen the example is a paper mill. So this is the classification of the load torque. Also, broadly you can classify, there is a broad classification of load torque. Broadly you can classify load torque into active torque and passive torque. So active torque is the load torque which has the potential to drive the motor under equilibrium condition. It has the potential to drive the motor under equilibrium condition. Now, instead of going on saying the definition, we can understand through an example. One of the main example is the torque due to the gravity. So if I have a particular crane, okay, so the crane is having some load over here and the crane is lifting this particular load. So what will happen? You have a gravity and the gravity is always exerting a downward motion. So your crane has to create a torque in the upward direction to overcome the torque of the particular gravity. And you can see that even if your particular hoist, even if it is moving downwards, still the torque due to gravity is again in the downward direction itself. Okay, so now here your crane will be exerting a braking torque such that it will not crash. Otherwise, what will happen, even if you exert a downward torque, again it will the particular crane, it will crash downwards. So in order to limit the speed of the particular load moving downwards, you can see a opposite force is being exerted by the crane. But you can see over here the torque due to gravity, it is always in the downward direction. It is always in the downward direction, and because of this you can see that even if the direction of the drive, even if the drive was moving upwards, the gravity torque was down, and even if it was moving downwards, the gravity torque was downwards. So you can see that the sign of this particular load torque does not change with the direction of the drive. With the direction of drive, it does not change. So the direction of the load torque does not change with the direction of the drive. It has the potential to drive the motor under equilibrium condition. Okay, so that is the active torque. What about the passive torque? So the passive torque is a load torque which opposes the motion. It is opposing the motion, and obviously the first type of torque that will come to your mind should be friction, or the frictional torque. So you can see that in the frictional torque, obviously your frictional torque is always opposite to that of the particular motion. Okay, and what about the direction of the passive torque? If the body is moving towards the left, I have a body over here and it's moving towards the left, the friction is always acting opposite. So you can see your frictional torque direction was towards the, if your body was moving to the right, the torque will be towards the left. And you have, if the body is moving towards the left, your torque will be towards the right. So here you can see that the sign of the load torque will change according to the direction of the drive. Okay, so the sign of the load torque will change according to the direction of the drive. So broadly you can classify load torques into active load torque and passive load torque. In active load torque, it will drive the motor under equilibrium conditions. So and that means it will retain the direction. No matter what the motion of the drive, it will always have a particular direction. It will not change the direction. Whereas in the passive load torque, the main example was the frictional torque. In frictional torque, you can see according to the change in direction, the direction of friction is also changing. So your load torque is opposing the motion of the particular drive. So these are the classification of load torque. We saw that you have constant, you had classified into 4. Apart from this 4 classification, we had also seen broadly 2 classifications, that is the active and the passive torque as well. So these are the classification of the load torques. Next we can move on to the components of the load torque. Components of load torque. So you mainly have 3 components for the load torque. So TL is divided into 3. You have the friction torque, you have the windage torque, and you have the torque required to do the useful mechanical work. Sorry, here load torque is with small l, and torque required to do useful mechanical work is capital N. So your load torque is classified into friction torque, windage torque, and the torque required to do the useful mechanical work. Friction torque, it is already understood. Your friction torque is something that is happening because there is a contact between the shaft of the motor and the various parts of the load. So whenever there is a contact happening, there is something called the friction torque. And friction torque can be further divided into 3. You have static friction. Okay, so TS is the static friction, or you can also call it as stiction. Okay, it is also called as stiction. Static friction or stiction. Then you have another division, that is friction torque is divided into static friction or stiction. Then you have the viscous friction. Viscous friction. So TV is the viscous friction. Viscous friction. And then finally you have another last one, that is the Coulomb friction. So you have the components of load torque, that is TL is equal to frictional torque, windage torque, and the torque required to do useful mechanical work. And the friction torque is further divided into static friction or stiction. Then you have the viscous friction. Then you have the Coulomb friction. And then you have the windage torque and the torque required to do the useful mechanical work. Now, what is static friction or stiction? Now, static friction or stiction is the frictional torque that is present during standstill. So, whenever the particular drive is in standstill, that time your stiction is present. And in order for the drive to start moving, it has to overcome Ts. Okay. So, for your drive to start motion, it must overcome the static friction. Only then it can start its particular motion. Okay, I hope it is clear. The static friction is present only during the standstill time, and in order to make the particular drive move, you have to overcome the static friction. And once the drive starts moving, the stiction will disappear. Once the drive starts moving, your stiction will disappear. It will not be present because it is present only during standstill. So that is the static friction. The next component of friction torque is the viscous torque. Viscous torque is a torque that is proportional to the particular speed. Okay, so you can see the viscous torque is proportional to speed. So in order to remove the proportionality, we have placed a constant, that is B. So viscous torque is equal to B into omega m. That is simply, it indicates that the torque is proportional to speed. Then finally you have a Coulomb friction. The Coulomb friction, it is not depending upon any speed, it is independent of the speed. It is a constant torque that is present within the particular drive. Frictional torque that is present, it is a constant frictional torque. Okay, and then you have the next component of load torque, that is the windage torque. Windage torque, we have already mentioned about one of the classification of load torque, that is the load torque proportional to square of speed. So this is similar to the windage torque. Windage torque is proportional to the speed square. So what do you mean by windage torque? Whenever a drive starts moving, the wind will generate a torque opposing the motion. The main example is a fan. Whenever the fan is rotating, the wind is providing a opposition to the motion, and this will create a torque. And that, using that example, you can say the fan is your greatest example. And from this example, you can see that the windage torque is proportional to speed of square. And you can see TW, it is denoted, you are removing the proportionality with a constant C. So C omega m square. Finally, you have the torque required to do the useful mechanical work, and this particular torque is depending upon the application. So we have discussed about the components of load torque. Right now, in the components of load torque, it is divided into frictional torque, windage torque, and torque required to do useful mechanical work. The frictional torque is further divided into three. You have the static torque, you have the viscous torque, and the Coulomb torque. Static torque, static friction or stiction is present during the standstill time. Once the drive starts moving, it will disappear. Then you have the viscous torque, it is proportional to speed. The Coulomb torque, it is independent of the speed. Then you have the windage torque. The windage torque is generated due to the opposition of the wind when the drive starts moving. It is proportional to the square of the speed. And then finally you have the load required to do the useful mechanical work. So these are the components of the load torque. And in our next video, we have come to the end of this video, and in the next video we will be dealing with the DC motor drives. So I hope this video was helpful. Thank you, and we'll be back with another video. Thank you.